Yeah, today I'll try to discuss about this Python package that we've been developing in the root team for our DataFrame distributed analysis. So the layout of the outline for today's presentation is roughly like so. I will present briefly what is our DataFrame, and then I will discuss the steps and the goals that we had in mind for a distributed version of such a tool. There will be some time for demonstrations with Jupyter notebooks on Swan, and I will show you later that. And then just to conclude the discussion, I will present you some performance numbers that we ran and a summary. All right, so our DataFrame is this Pandas DataFrame-like high-level interface to high-energy physics data. It features a declarative interface, and with this declarative interface, you can define a set of operations to run on an input dataset, and our DataFrame supports various data sources for to that purpose. And in the end, the set of operations that you have defined will actually be executed lazily. That is, they will be accumulated in the program and not run until the moment where you actually need the final result. At that moment, all the computation graph that results from the operations that were requested will be executed in one go on the entire data set. So the final result will finally be retrieved. And the goal with this interface is to provide an easy to use way to process high energy physics data across the board. And for that, in this slide, I also leave you here down the reference guide and some tutorials that you can check out for yourselves if you're still not familiar with our DataFrame. Now, our DataFrame itself has natively support for exploiting all the cores available on your laptop or on any single machine. So it does that through implicit multi-threading that is available in root. But there's another goal that we had in mind, and this goal was to enable interactive and large-scale data analysis with our DataFrame, but distributing the workload of the analysis to a set of resources that might be remote, outside of your own laptop. So in order to do that, we needed to separate a bit the roles. So the ourDataFrame computation graph that I previously described is built locally, and then the workload that's represented by this computation graph will be distributed to a backend, to a kind of distributed framework. For example, we already have some working implementations of connecting to an Apache Spark cluster and also a Dusk cluster. And these are the two backends that I will show today. But the design of this Python package that we have created is modular. And in fact, many other backends could be created and implemented in a way that it would allow our DataFrame to plug in to any of these distributed frameworks. For example, we are also developing another, with an external contribution, we are developing a backend for AWS Lambdas, so running the ourDataFrame computation graph on these serverless functions. But that's not the topic for today. Today, I will just discuss the first two that you see here. And the final goal for this is to have everything from start to finish in the same interface. So you don't need to, take your time to launch the job and then wait for the partial results and then merge the partial results on your own. Everything is done in the same Python program in the end. And how does it look like from the perspective of the program, so the user? In this slide, I wanted to show you the main differences between writing and creating and running an ourDataFrame analysis locally on your single machine. And this is what you see on the left. And then on the right, I try just to highlight the few differences that are needed in order to turn this Python program with ourDataFrame into a distributed execution. So on the left side, let's start with importing the class that is ourDataFrame, and you can just import it from the root package. And then whenever you have imported this class, ourDataFrame supports some constructors, and you can provide the arguments to these constructors directly from Python. Even though ourDataFrame is a C++ class, but we'll get to that later. So in this case, you see that there are two constructor arguments. The first one is just the name of the dataset, and the second one is the name of the file where the dataset is stored. And let's quickly jump over to the right side here to see how to turn this into a distributed analysis. You will see that the differences are very minimal. The thing that you need to do is that instead of importing directly ourDataFrame, you need to tell root that you want to use a distributed ourDataFrame. So these things live in their own root submodule. For this example, I just wrote the code to retrieve a Dusk ourDataFrame. So you see there's distributed.dusk.ourDataFrame. And you can just, for easiness, you can just store into a variable. So later calls to ourDataFrame will actually point to the distributed ourDataFrame class. And then the extra step that you need to do is whenever you're creating the ourDataFrame, you just need to provide it with a way to connect to the Dusk cluster in this case, or the Spark cluster in another case. If you're already familiar with any of these distributed frameworks, for example, Dusk, you will know that you can create these client objects, and these are just Python objects that allow you to connect to the Dusk cluster. And then the ourDataFrame constructor, of course, will always accept the same arguments as the local ourDataFrame constructor, as you can see here, the name of the dataset and the file name, but it will also accept an optional argument for this connector to the distributed cluster. In this case, we have a Dusk client optional argument that will accept an object of type client from the Dusk library. As you can see, there's a third box down here, and it's just one, it's not two. And the reason for that is that apart from pointing it to the right ourDataFrame class and connecting to the Dusk cluster, everything else in the program stays exactly the same, from local on a single machine to distributed execution on hundreds of nodes. There is no extra step needed in the code to retrieve your final results. So that's what happens in the program itself. But behind the scenes, the creation of tasks for these distributed resources is actually done in this way. So in this image, I just wanted to show you that on the client side, we are creating the tasks that will be sent to the distributed resources. And we are doing that by splitting the input dataset into some ranges of entries. And we take care that the ranges do not overlap one another. So this is just a list of pairs of integers, right? And this list will get sent to the distributed resources. Each element of the list, each pair will create a task. And each task will be run in one of the machines of the cluster. One of the important things here is that the tasks will never overlap, also with respect of the reading. So it's not like each task will have to read the full data set. It will just have to read the particular entries that were assigned in the range, and this also avoids extra overhead. So now that what I just showed with this distribution of the tasks is, generally speaking, what any backend in distributed ourDataFrame should do. But it also, of course, needs to be actually implemented. And here in this slide, I wanted to highlight some differences in the implementations that we found when dealing with Apache Spark or with Dusk. Well, simply speaking, we are always creating a sort of a MapReduce tree pattern in the execution of the tasks in the distributed resources, something that you can see here on the right side of this slide in this image. So there will always be a set of mappers. In this image, only the first vertical set of nodes is the mappers. And then all the other nodes in the distributed computation graph will be reducing nodes. So nodes that take the partial results of the mappers and then reduce them until there is only one final result that can be sent to the user. That being said, this similar distributed execution is, well, it's just adjusted to the API of the backend itself. For example, with Dusk, we needed to use the delayed objects, or with Spark, we just used the native Spark API. But in the end, what we create is what you see here in this image, a set of mappers and all the reducers that just need to merge the partial results. One other difference between these two backends in particular is that Apache Spark processes everything in stages. So with Spark, you get all the mappers that execute all their work, and then at a separate stage, you will just reduce these results. On the other hand, Dusk can reduce two mappers that have already finished their work without waiting for all the other mappers. So that happens more in a more dynamic way. But these are, just implementation details. The important message is that we're always creating this computation graph that follows like a tree pattern in the end. And another key message that I wanted to discuss is the following. So with ourDataFrame, we are able to connect to Apache Spark, Dusk, or any other kind of backend through their Python interface. And we do the same with ourDataFrame because Root offers a Python interface that's called PyRoot. So we can glue the two interfaces together. But in reality, when we are in the distributed resources and we are running the operations that the user asked, we are actually running C++ code. And the C++ code does mostly everything, like the bulk of the operations, the computation graph and the IO, everything is executed in C++ thanks to Root and its interpreter. Okay, so that was a general introduction about distributed RDataFrame, and now it's time for a demo. So for the demo, you can see in this slide a link to the notebooks that I will show you. There's a GitHub repository, and this GitHub repository will also have a little badge. Probably I can already show you this way. So if you go into this GitHub repository, you will see a badge down here to open this in Swan. I have already opened my GitHub repository in my Swan session. Swan is this service for web-based analysis that CERN offers, and you can see it as this interface, which is quite similar to the Jupyter Notebook interface, and it's very nice for to execute these notebooks that we already had in the repository. So with the demo here, I want to follow a physics analysis example that we have here. And I want to show you how this example can be run locally with ourDataFrame and then with distributed ourDataFrame, both on the Dusk, with the Dusk backend and with the Apache Spark backend. So the analysis itself is processing a single file that stores 61 million entries. These events were recorded by the CMS experiment in 2012. So the analysis itself is an open data analysis that you can find also links to in the notebook itself. And here we are just starting with importing root, and then we need to create the ourDataFrame object. Again, this ourDataFrame object is actually at its core is a C++ class, but we are accessing it through Python thanks to the PyRoot bindings. And you can see that we have two arguments to the constructor of root RDataFrame. The first one is, again, the name of the dataset, and the second one is the path to the dataset itself. Once we have constructed this RDataFrame object, we would need to analyze it. There is a particularity in this notebook that since we are running locally and we don't want to run on 61 million entries because that could take a while, we can just tell ourDataFrame to only operate on the first million entries. And we do that through the range operator here in operation on ourDataFrame. And then we are actually starting the real analysis. So the analysis is made of the following steps. The first steps are filtering the dataset, and you can see them in this cell here, filtering the dataset from unimportant events. And then whenever we have the important events left in the dataset, we want to define a new column. And this column will be the result of an operation that's made on other columns of the dataset. This operation is actually written here, and we are calling from PyRoot, from Python, from this Python interface, we are calling a function that is inside a root namespace. So this function is actually a C++ function that's implemented inside root. And we are creating a new column in the dataset thanks to this define operation in our DataFrame. And then finally, we want to retrieve the final result, which is the histogram, an histogram of this column that we just created. Now, if you haven't noticed so far, we never got a cell that was running for a noticeable amount of time, and that's because, as I mentioned previously, our DataFrame just runs lazily. So until we request this histogram, which is the actual final result that we want, we will not see anything running. That happens, the request of the histogram happens in this cell, so I can execute the cell and wait a few seconds for my result to come back. Okay, here it took 3 seconds. And then finally, I can plot the resulting histogram in this other cell with JS root that enables these plots directly in the cell, in the cell of the notebook. Okay, so this is the final result of the analysis in this case. I want to reiterate that this result does not contain the full dataset. So we didn't process the full dataset, but we just processed the first million entries. Now I will move to another notebook which has
Vincenzo.
Yes.
Sorry. Yes.
Yes.
Couple of. I know. Oh, very sorry. I mistake with time. I think you have actually 12 minutes. Sorry.
Okay. So I will move to this other notebook. This is the same exact analysis as we just saw, but I'm going to use what's it called? I'm going to use Dusk to distribute the execution of our DataFrame in this case. So and in this case, I will be able to not just select few entries from my dataset, but actually run on the full dataset. Now, to do that, let's see only the differences between the two notebooks. So one of the key differences is here in this cell. We are creating the object that is the object that will allow us to connect to the Dusk cluster. And this object is the client object that you see here. We are connecting to a cluster of Dusk machines of Dusk agents that we have created specifically for the purposes of this demonstration. And so we have it available in the CERN network with 16 workers and 16 cores in total. Now, with this client object, we can go and create an RDataFrame that will be able to actually distribute the execution to Dusk. And to do that, we just need two more things. The first one is to tell root that we want to use the dusk.rDataFrame class, and then actually create that RDataFrame using the first same two input arguments as the RDataFrame of the previous example. And then we have another two optional parameters. The first one is called end partitions, and it's just the number of tasks that we want to run. So in this case, we are running 16 tasks. That means that each core of our distributed cluster will have its own task to run. And finally, as I mentioned in the slides, we need to give it the client object. So the object that will allow us to connect to Dusk. And whenever we have done this, we have created the RDataFrame. All the rest, all the cells, they are exactly the same as the one that I just described. So I won't go through them again. We are creating this new column and trying to create an histogram. But this time, whenever I trigger the execution of the creation of the histogram, it will not be executed here, but as you can see, if I move to this other tab, it will be executed on the Dusk cluster. And this is the tree pattern of the MapReduce execution that I mentioned previously. And in this Dusk dashboard, we can see, well, it's probably already over, but we can see the status of the cluster, and we can see that Dusk was able to run these mappers, these tasks quite fast. So if we go back to the notebook and we try to plot the result, we can see that now we have the full data set having been processed, and the plot that comes out of that is available for us. And we didn't process just 1 million entries, but the full data set. So as a final demonstration, let me show exactly the same thing, this time using the Spark cluster that CERN offers. So in order to do that, we already have a graphical interface that allows us to connect to this Spark cluster in Swan, and it's here where the Apache Spark symbol is placed. And then we can just connect to the cluster with this connect button here. I chose to have 16 cores in total, again, the same as the Dusk example. So connection just takes a few seconds usually. And whenever it's connected, it will tell us that we can go back to the notebook and that it also has created, okay, here we are. So if we go back to the notebook and we, okay, start with importing root as usual, but then what I wanted to show here is that the connection to the Spark cluster is given by an object that is called a Spark context. In this case, since we connected to this cluster thanks to the graphical interface, we already have a Spark context provided for us in the notebook, and this is provided by Swan. If you had your own Spark cluster, you could just create the Spark context on your own, and everything else would work just the same. So again, we need to create the RDataFrame. So we point RDataFrame to the correct instance. In this case, we have a Spark RDataFrame. And we can create the RDataFrame with the same constructor arguments, but this time we're not using Dusk client as an optional argument. We're using Spark context because, of course, we're using Spark. So we create the RDataFrame that can run on Spark. The rest is exactly the same. Again, I won't go through that. And we come at the cell that triggers the distributed computation. So whenever I'm in this cell, I can start executing it, and Swan will start to provide us with a Spark UI down here. So we don't have a dashboard in another tab, but we have it just here in the notebook itself. So in the Spark UI, we can go see the actual Spark tasks being created and started. So you see some of the tasks are already there. And we just need to wait for the Spark executors and the Spark workers in general starting to address the tasks and run them distributedly. Whenever a task is over, we can see that they start turning green. And in a few seconds, we should be already seeing the completion. Okay, exactly. There we go. And finally, we can already plot here the final plot. So we have just showed we've just shown the differences between running an RDataFrame analysis in a local notebook, so in a notebook local to your machine, or in a notebook that connects to a Dusk cluster, or in another notebook that connects to a Spark cluster. And the differences in code were actually quite minimal. So now we can just go back to the slides for some final remarks. And I have some numbers to show you. All right, let me, okay, I can switch back to full screen. So that was a demonstration, but we also ran some numbers to test the performance of the two schedulers. I created, as I mentioned previously, a cluster of Openstack VMs. In total, we had 13 VMs. All the VMs have the same configuration that you can find here. One was reserved for the Dusk scheduler or the Spark master, and the other 12 VMs were always reserved for running the Spark or Dusk applications. The dataset itself and the analysis in general is exactly the same. The only difference is that I replicated the dataset 100-fold to reach a dataset size of 210 gigabytes in total. And this dataset is being fully processed. So all 210 gigabytes are processed by the Spark or the Dusk agents whenever I run the distributed RDataFrame application. And let me just show you the results of these performance numbers. So in this slide, I am showing the average execution time of the run of the analysis with the increased data set with the Dusk backend of distributed RDataFrame. On the left side, you have the absolute runtime. These are averages over 3 measurements for each of the data points on the x-axis that represent the number of nodes that were used as agents, as workers in this example. And on the right side, you just have the same numbers but turned into speed up. So the speed up compared with executing this analysis on only one node. And if I go to the next slide, I will just show you the same plots, but this time with Spark. As you can see, between the two schedulers, the difference is not that great. Spark seems to be a bit better on the speed up point of view, but it's also maybe because we had this slightly higher runtime in the execution with one node. So we wouldn't say that there's a real gap between the two executors. schedulers, sorry. And just as a final comparison, I have this other plot where I show the full distribution of the points of the benchmarks that I ran side by side. You have the blue circles that are representing Spark and the yellow circles that are representing Dusk. And as you can see, both distributions, maybe except for this first point, but all the others, they reach quite a similar runtime. So that's exactly what we want. So in summary, I have presented you ourDataFrame, which is Root's declarative interface for data analysis. And since the latest Root release, which is 6.24, ourDataFrame can also run on distributed frameworks, such as Apache Spark, for example, requiring minimal changes with respect to a local application of ourDataFrame running on a single machine. And for now, we have, I've also shown the implementation of two backends today. One is Apache Spark and the other is Dusk. There will be also other backends coming in the future, and stay tuned for that. So I also leave you in this slide some useful links, the guide to ourDataFrame and a tutorial if you want to try out this feature for yourself. So yes, that's it from my side. So if you have any questions, I should probably see on Slido actually, right?
Exactly.
Cool. Let's see. All right, so I'll start from the first one. Is it possible to use ourDataFrame with multiple T3s and the same number of entries? So if you're referring to using ourDataFrame, for example, with the friend trees, yes, that is definitely possible. I mean, traditional ourDataFrame, the ourDataFrame that runs locally, has support for that since many root releases. Distributed ourDataFrame is also supposed to have support for that. If you tried and you find anything that's not working as you would expect, please let us know by contacting the root team or submitting a GitHub issue. Yeah. Do we have to do something whenever I answer? Like, no, just leave it there? Not sure.
Yeah, leave it. Yep.
Okay. Cool. Question about distributed RDF. How does it compare with going to batch, like htconter? To process large data set, I had to go to batch. So curious to try. That's a very good question. It's actually an alternative to going to, so you know, batch systems and interactive analysis systems like Spark and Dusk, of course, they have differences and they serve different purposes. But you are right in thinking that both are ways of distributing your application if you have a very large data set and you want to process a very large data set. One added benefit with systems like Spark, Dusk, and in this case, distributed ourDataFrame, is that you can do everything in the same interface. So you don't have to submit your jobs, then wait for the partial results, merge the results. You cut that middle step, and you just have everything in your own Python program or Python notebook, and you will get the results straight away there. Okay, so next question. What are other applications of RDF besides using CERN Open Data? Well, I would say that ourDataFrame is suited for any kind of data. I mean, I have also shown a slide here. Let me go back there. So in this slide, for example, I was showing that ourDataFrame has support for different kinds of data sources. Of course, you would need to adapt your, I'm not sure about the data source that you have in mind. If it's in this list, probably ourDataFrame will support it. If it's not in this list, it will not be supported, but you can always make a request for adding a support of a data source, since different data sources can be added and supported in ourDataFrame. So far, with distributed ourDataFrame, we have tested it with the T3 data source, which is Root's default data source. We haven't tested it with other data sources. Maybe in the future we could also think about that, but keep in mind that for now, distributed ourDataFrame is an experimental tool inside the Root framework. So some things might still be missing, of course. All right, so Next one. Is data read from EOS by each node separately? IOW, do IO bound analysis get a speed up? Yes, definitely. As I was trying to explain in this other slide, what's that? This one. So distributed RDataFrame works in such a way that each of your tasks in the distributed resources will read only a specific portion of entries. Let's say your dataset has 100 entries and you just want to read the first 10 entries in a task. You will not read the full 100 entries from your dataset in that task. You will just read 10 entries. And yes, you will also read them remotely. But again, you will not be reading a full file from remote, but just that particular range of entries that you like. And this avoids extra network transactions, of course.
Let's go with the last question, and then in case we can move to Slack. So, yeah.
Okay, thanks. So last question then. Is it possible to use precompiled C++ defined filter kernels? This is a very good question. We are actually actively discussing and working on that. Currently, ourDataFrame supports, as you have seen in the slides, passing strings, and these strings need to have inside them valid C++. So whatever you pass in this string, and if it's valid C++, it will be turned into a C++ lambda and just in time compiled. But the direct answer is that ourDataFrame runs C++ code. Now, an added side to this question is whether you could run maybe also Python functions and pass them to these defines and filters. And that's something that we are still trying to figure out. Traditional RDataFrame has support for something like Numba that is used to actually wrap these Python functions and be able to JIT them. Distributed RDataFrame still needs some work on that side, but definitely you will always get your RDataFrame running C++ kernels, even though you access it from PyRoot.